Moving on with Chapter 8, we are now going to learn how to calculate enthalpy changes for processes. So the principles we're going to learn in this chapter that are new, and incidentally, these are fair game for concept questions, and you should know them. So this is not something that you can just say, oh, I wasn't paying attention, or I forgot. No, you have to learn these things. Okay, so you should be able to state what is the normal boiling point. You should be able to explain constant pressure heat capacity, constant volume heat capacity, heat of vaporization. And learning outcomes for this lecture specifically, we are going to learn how to calculate the energy balance on a system with a pressure change, and we're going to learn how to carry out the energy balance on a system with a temperature change using heat capacity. We are still not going to consider chemical reactions until Chapter 9. So considering the situation where the temperature stays constant, but you may have a change in pressure. For gases, especially ideal gases, but almost true as well for real gases, the enthalpy change is only dependent on temperature. So if the temperature stays constant, even if the pressure changes, that delta H is equal to 0 for that process. We could say the same thing for delta U if it were a closed system. On the other hand, for liquids and solids, the internal energy of liquids and solids is nearly independent of pressure at constant temperature, as is the specific volume. So let's look at our relationship for enthalpy. Remember, delta H is composed of internal energy plus the flow work. So if we have a constant specific volume when the pressure changes, then this term will be 0. If we have a constant internal energy when the pressure changes, this term will be 0. And we are left with delta H is equal to V delta P. So this is how we will calculate the enthalpy change for a process that has a constant temperature but a changing pressure. And specifically, we do that for liquids and solids, not gases. Okay, so an example of a process that this would apply to is pumping of a liquid. So as you remember, the pump work minus W dot S is equal to M dot delta H, and that is going to equal M dot times V delta P. So here's a question for you to think about. Which V should be used? The initial V or the final V? Well, we just said that the specific volume doesn't change much with pressure, so you can use the initial or the final. It shouldn't matter. They should be the same, approximately the same anyway. So here's a calculation for us. We are going to pump a liquid at constant temperature, 50 degrees, from 1 bar to 200 bar. So let's compare the calculation using delta H equals V delta P and reading the enthalpy values off the steam tables. So if we look it up, the pressure here, we can get the volume. We need to get this volume. And at 1 bar and 50 degrees C, the specific volume is given, and H hat is given as well from the steam tables. So we can calculate V delta P using that specific volume times the difference in the pressure, 200 bar minus 1 bar. And then we're going to convert from bars to pascals. And by doing that, we will then have our result in joules per kilogram. So now if we want to compare it with the value on the steam tables, we'll make it kilojoules per kilogram. So let's compare that with the value we get at using the steam tables. Okay, so P is equal to 200 bar and 50 degrees C. H hat is given from the steam tables, and that would be remember the state of our liquid at that point? Compressed liquid, not saturated. This is not a saturated liquid. Okay, so the delta H of our process then is 17.1. So you might think that's relatively off, 17 versus 20, but in fact, that it gives us a very good approximation of the difference. Now let's talk about temperature changes. You remember heat capacity from chemistry. So we learn two types of heat changes. Okay, sensible heat, the word sensible heat refers to changes in temperature of the system. Okay, so these are definitions. The change in enthalpy with respect to temperature at constant pressure is defined as Cp, the constant pressure heat capacity. On the other hand, the change of internal energy with constant temperature, the change of internal energy with temperature at constant volume, we define as Cv, the constant volume heat capacity. These are defined based on thermodynamic variables, and we will explain why we choose constant pressure and constant volume for enthalpy and internal energy respectively when we get to thermodynamics. But for now, these are the definitions, okay? And if we separate the variables and integrate, we now have delta H is the integral from T1 to T2 of Cp dt. And delta U is the integral from T1 to T2 of Cv dt. So again, for open systems, we are going to be using delta H. So here's the question. When does delta H equal Cp delta T? And you can think about that, and we'll discuss it in class. Okay, so now, does the heat capacity depend on temperature? Usually it does, especially for large temperature changes. So it depends not only on temperature, but also on the state of the system. What does that mean? It's going to depend on whether it's a liquid or a vapor, okay, or a solid, of course. For ethanol, we look for the functions that tell us what is the heat capacity as a function of temperature. For liquid, we can find this value, and for gases, we can find this value. Where do you find these? You will find them on table B.2 in the back of your book. Okay, so if we use that table B.2, it will tell you that the temperature should be in Celsius. Okay, so we can calculate the delta H for 1 kilogram of ethanol to be heated from 25 degrees C to its normal boiling point. Let's do the calculation. This is a liquid, okay? So we have Cp is written here as a constant, okay? But we notice that we have this in the denominator. So if we integrate Cp dt, we will have the expression of this constant here times T2 minus T1. Very, very simple math. Okay. So then we can calculate the delta H of our liquid between our two temperatures is going to be 6.01 kilojoules per mole. Okay, so we haven't multiplied yet by the kilogram of ethanol. All right, so here we can include our kilograms of ethanol in this calculation. All right, we have kilojoules per mole, and if we get rid of the grams in there, and we're going to get rid of the moles in there, then we have a final value, delta H of our liquid, of 130.53 kilojoules. Okay. Next, let us calculate the value for the vapor. We're going to go from 78.5 to 90 degrees C. So when it's a vapor, we are going to use this expression, also from table B.2. And now we have a slightly more complicated, but still, you are all quite capable of making this calculation. Okay, one thing I want to point out is that delta T squared does not equal T2 squared minus T1 squared. Okay, you have to square the individual temperatures and subtract them. And you have to pay attention whether they ask you to do it in Celsius or Kelvin. Use Celsius or Kelvin, depending on what the table where you find these constants is. Okay? All right, and then we get rid of the kilograms, and we now have 18.43 kilojoules. So when we calculate delta H, the reference state falls out. So we don't really need to think too much about it. If you're getting it off of tables, then you need to pay attention. So now, if we were to calculate the delta H for water to be heated from 25 degrees C to 9 degrees C, okay, initially water is a liquid, and then, so we calculate, oh, I'm sorry, we're talking about water. Okay, so from 25 degrees C to 90 degrees C, water is a liquid. So we can get the delta H, and we can get the values from the steam tables. Okay, here we are, now we have it in kilojoules. All right, so now, reference state for the enthalpy calculations. In calculating delta H, again, we don't need to worry about a reference state, but if we're calculating the enthalpy of a system, we do need to worry about the reference states. So it's a difference between, I'm talking one thing is delta H, and another thing is H. So you can calculate your system enthalpy, H, okay, by integrating from the reference temperature to your system temperature and doing CPDD. How do we do that? It's exactly the same calculation as we did to calculate the delta H from an initial temperature to a final temperature. You simply plug in the reference temperature as the initial temperature. Now, we learned how to go to heat up a liquid and how to heat up a vapor, but we have not learned how to heat up a liquid and what the total delta H for the entire process is, because we've ignored, until now, this heat of vaporization. So this heat of vaporization can be found on tables, and our table B.1 has the delta H of vaporization for species at their normal boiling point. What is a normal boiling point? It is the temperature at which the species boils when it is at 1 atmosphere. Okay, so you can look this value up on the table at its normal boiling point. Okay, and now if we do this, the same thing for our kilogram, we end up with 837.42 kilograms. So now, if we want to calculate the change in enthalpy to raise ethanol from 25 degrees C as a liquid to 90 degrees C as a vapor, we have to use all three values. Okay, the delta H of the liquid, the delta H of the vapor, and the delta H of vaporization. And they're all going to be positive. Note that. Okay, which one is the biggest? The vaporization. It takes a lot of energy to make a gas out of a liquid. Okay, so we can also approximate the values for the heat of vaporization. If you cannot find it on a table, all right, then we can calculate it. The first value here, the first equation here is Chen's equation, and it is used to approximate the value of the delta H of vaporization at the normal boiling point. Okay, so you have to look up the critical pressure and the critical temperature, and where do you find those? Table B.1, all right, and you calculate them. TB is the known normal boiling point, and then you have to make those ratios of TB over TC. If you have one value of the delta H of vaporization, say the value from table B.1 that's at the normal boiling point, then you can calculate the delta H of vaporization at a different temperature from the normal boiling point using the Watson correlation. And this is a very simple ratio calculation. This, again, is the critical temperature. And we make this calculation, and we raise this to the 0.38. It's just an empirical number, but it works reasonably well. So to summarize this lecture, we have to be taking account of changes in temperature because it results in a significant energy cost. And we will use heat capacities. We will use CV for closed systems at constant volume. And for all open systems, and also, and I didn't explain this, but we will also use CP for open systems that are at constant pressure. Okay, for a phase change, we need to include the heat of vaporization to go from a liquid to a gas, or from a gas to a liquid if we're cooling. And we have ways to estimate values of the heat of vaporization at different temperatures. So finally, I would like you to do this problem. And this is a problem where you're going to have, we're starting with hexane as a vapor. We have 15 moles per second, entering an adiabatic heat exchanger. Okay. Now, the Q of, I'm drawing this incorrectly here, actually. It's adiabatic. There's no net loss of heat, but there's no net loss of heat from the entire heat exchanger. But the hexane is going to lose 915 kilowatts to the cooling water. Okay, so the heat exchanger itself is adiabatic, but we need to we're losing heat from the hexane. So we're only considering as our system here. Our system is just the hexane, and it is losing heat to the cooling water. So it's going in at 200 degrees C. It's coming out as a liquid at some unknown temperature, but we know how much heat has been removed. So using the information we had from this lecture, you can determine what is the final temperature of our hexane if it loses 915 kilowatts.